This is the ROS Developers Podcast, episode 84.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that give you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and today I would like to dedicate this episode to all those pioneers that are around there building industrial applications with ROS2. So I think that's a very tough position to be, because this is a very uncharted territory, and it is very hard to get actual results there. So I think that area is for the really brave ROS developers out there. So you are making ROS2 a reality in the industry, and then I would like to say thank you for moving forward the frontiers of ROS2. This episode is dedicated to you guys out there. Today, we are going to talk with some guys from Southwest Research Institute and ROS-Industrial. And they have been doing just exactly that, building hybrid applications with ROS1 and ROS2 on industrial robots. How amazing is that? So we are going to talk with these guys and learn how you can also do the same results, get the same results by practicing with the software they have created. But before going into that, let me remind you about our online academy. It's called the Robot Ignite Academy. And in the Robot Ignite Academy, we have an academy for learning about ROS and robotics, and ROS applied to robotics. So you can see here that we have a lot of courses related to robotics theory, then also to basic ROS, and also navigation. So all the subjects that you can think about: perception, robot creation, manipulation, artificial intelligence, and everything with your favorite robot framework, of course, is ROS. There are also courses about ROS too. Check yourself the academy. I will put the link on the show notes. Okay. So then now it's time that we go and we talk with the two people that we have here today with us from Southwest Research Institute. So we have. Let me introduce you, Joseph Schornak and Jorge Nicho. They are both research engineers at Southwest Research Institute, and they are in charge of software development for robotic systems in industrial environments. They are here today to talk about the hybrid ROS1 plus ROS2 system for industrial robots that they have built. So welcome to the podcast, guys.
Thanks, Ricardo.
Thanks,
Great
Ricardo.
to be
here. Yeah, great to be here too.
Okay, great. My pleasure. So this conversation started because we were talking on LinkedIn, I think, with Matt about ROS Industrial and how ROS2 is applied in ROS Industrial, and he suggested, hey, we are doing very, very cool stuff here, so you had to talk to these guys here, and he suggested me to talk to you. And so I would like to start asking you, how long have you been programming with ROS?
Sure, I can start with that one. Yeah, I have been programming with ROS for about the past 4 years. I got started kind of as I got into grad school for robotics. And then I've actually been mostly focusing on ROS2 for just under the past 2 years. So I got started in ROS2 Crystal, and now we're working with Eloquent and Foxy.
Uh-huh.
So as far as I'm concerned, so I started working for Southwest Research in 2011, and pretty much from the very beginning, I started working with ROS. At the time, I believe it was ROS Electric. So I've seen the progression of ROS, right, from Electric to Indigo and all those different versions, and the adoption of ROS into industrial systems has matured quite a bit. And as far as ROS2 is concerned, I've started using it basically for about a year now. and I've seen, a couple of different versions of ROS2 being used in applications.
Okay.
So in total, I'd say it's probably been about 10 years almost of ROS development.
Wow. Okay. So here we have two so I can say that two real ROS developers there. So here, and then you have, with this experience in your pocket, so you have developed an industrial application, and this industrial using ROS, this industrial is called the collaborative robot sanding. Can you explain to the audience what is this collaborative robot sanding?
Sure. So it is a project that's sponsored by the ARM Institute, if you're familiar with it. So Advanced Robotics for Manufacturing Institute in the United States. It basically involved, three different organizations, Southwest Research being one of them. Then the other ones were Spirit Aerosystems and NIAR from Wichita State University. So the goal of this application is to empower workers at a factory floor by leveraging robotic, breakthroughs in robotic technologies. And so specifically for this application, that means this robot is a collaborative robot, is a UR10 robot, which has a number of collaborative features, will assist an operator in sanding aircraft panels, right? So the human guides the robot into, what parts of the sanding or of the panel have to be sanded, and the robot will respond to the operator's guidance so as to complete that task. And it basically, for the most part, it was developed in ROS2, right? So most of the logic, the perception, the motion planning, a lot of those, core components for this application were built in ROS2. But there were parts of it that needed to be developed in ROS1 because, ROS2 is still, a work in progress, and there are various.
Okay, it looks like we have lost connection with Jorge. So he was explaining.
Sorry.
Oh, here he is. Great. We got it back. So you were explaining, Jorge, that you were explaining that you needed to build a hybrid application because.
Yes, sorry about that. It cut off on me. Yes, because there were parts of ROS1 that haven't yet made its way into ROS2, haven't been ported yet. In our case, it was the robot driver, right, for the UR10. So we needed to bridge that component. So by bridging, I mean we create this bridge component that allows a ROS2 application to talk to a ROS1 node, right, and in order to stream joint trajectories into the robot controller. So that's where the hybrid part of it comes into play. Okay,
wait. Don't explain everything in the introduction. Let's keep something for the middle of the episode and this. Sure. So I think that with your explanation, so the audience has an idea of what this collaborative robot sanding is about. And can you tell us when was it released? Because I have understood that it's been released very recently, right? So it's state of the art.
Yes, the project just concluded about a month ago or so. So the actual repository or repositories have been available on GitHub for about a year now, right? But they've been evolving and changing because the project was still ongoing. But yeah, the project itself is available in GitHub along with all the instructions needed to build it and run it.
Okay.
Right? Obviously, there is an actual physical system that goes with that project, right? But obviously, most people who were not involved in the project and want to test it out, they can run it in simulation. So it can be used with Gazebo to simulate that whole process.
Okay. Yeah. So that there is a possibility for the audience to download your project and practice and test it and see how it works in the simulation that you have also built, right?
Correct.
Okay. Correct. And then let me ask you, what was the purpose of building this this project? So this sanding, I mean, so I know that it's sanding those pieces and so on, but was the final end, or was there another meaning why you decided to build this project?
So I guess the larger goal of such an application is to empower, operators on the factory floor to basically do these, repetitive sanding tasks by leveraging, the capability of robots, motion planning and perception, things like that, right? So in sanding, there are a lot of repetitive tasks that operators do nowadays, and so if you were to have a robot with sufficient capabilities for detecting these parts and running these sanding toolpaths, then you'll be able to save a lot of time in doing those mundane repetitive tasks. And so it's basically the goal of it is to have increased productivity of the workers by leveraging robotic technologies.
Okay, and then another question. So from the point of view of the user that is using your system, not from the developer, so how does it work? So what there is an operator there, what does it has to do?
Sure. So when you first run the application, you see a GUI, right? It's basically RViz, and there's a panel that has been built that talks to the main application. So this panel is a very simple panel. It shows you the current state that the application is in. It also gives you some buttons to be able to step through the various steps of the process.
And wait a second. When you mention about the state of the application, you mean that we can see the robot itself there, right? How the system thinks that the robot is in which position, and
yes. So there is, obviously RViz, as you know, has a 3D visualization.
Correct. Okay. We had another.
He'll be back.
Okay. Yes. So yeah. So
okay. Sorry about that. I'm back again.
Yeah, we got you back.
So there's a 3D visualization window in RViz, and it allows you to see the state of the environment, right? So that's the graphical state. But at the same time, the application itself has an internal workflow to it, where each step in that workflow is a state. And so this GUI, this panel shows you the actual internal state of the application. So that way the user knows where the application is at internally, right? So beyond the 3D visualization.
So it's not only seeing the actual robot where it is, but also the state of the internal application.
Exactly.
And what does that he has to do? Okay. So he can see that and so on, but he can.
So the user will, through that panel, he will advance or step through the various states. So let's say, the system just started. The first step is to register the aircraft panel part. Right. So there's a scanning state that the robot goes into, or the application goes into. So he'll just click a button to go into that scanning state. And then the robot will do all the heavy lifting, meaning it'll move through various predefined scan poses, capture, scans with a camera that is mounted on the robot, and then move to various scan points and collect an aggregate point cloud, which will then be used to register the location of the part in the work cell. So that's what the user can do from the application by just clicking a button that says, go do the next logical step in the application.
Okay.
So that's one step, but there are multiple other stages in this application.
Okay.
And in the same way, he will step through those by clicking one button to
after another.
Through those.
Okay. Yeah, I wanted you to explain that because I wanted to show that the application is actually quite complex. And it has to interact with real physical objects in the real world. So it's not a simple thing. It's just not just a software thing that captures and then processes and gives a result. So it's quite a complex thing.
So one thing I think is important to emphasize here actually is how the system is different from kind of existing, quote unquote, traditional industrial robotic systems. My kind of go-to example system for an industrial robot is a robot in a car factory, right? And those robots there, the parts are all very carefully, precisely positioned on fixtures and jigs. So the robot is always doing basically exactly the same motion every time, maybe with some little adjustments to like line up where welds need to be positioned and that kind of thing. Whereas in the collaborative robotic sanding application, the first step is that the part is just on this big rolling cart, and the operator just sort of pushes it into the work area of the robot. It's not really precisely positioned at all. So when Jorge described the scanning process, the first step is the robot has to figure out where the part even is located in the environment in order to do this work.
Scan.
So
okay.
Yeah, so that's kind of a common theme with a lot of the projects that we've worked at Southwest Research Institute. We call them scan and plan systems. So we scan to build up a model of unknown geometry in the environment, and then we plan to do some process on that geometry.
On it. Okay. So that's a very good clarification. So it's indicating that the system is even more complex than we thought. So it's not that the operator is putting the part on a very, very specific location and orientation, but it's basically putting there the piece. It is, and then this scanning part is the one that is creating the model of how the piece is located on a space, and then progress from that point. Okay, great clarification. And then for developing this application, so which elements did you have to develop? You have already mentioned some, for example, this interface based on RBAS for the operator, and this scanning part component. But can you describe kind of a list of available of parts that you had to develop? Maybe, Joseph, you can take the lead now that Jorge...
Sure. Actually, Jorge is here, I think.
Okay, then go ahead, Jorge.
Sure, yeah. So I guess there were about 4 major components, right, other than the GUI, which you described. So those were essentially the perception part. One of those is the module that allows us to find where the part is in the work cell. Right, so that was developed using the point cloud library, which takes sensor data and runs an ICP algorithm to be able to match or find common features between, a part geometry and the point cloud that you sense by taking pictures from the environment. So that was one component that we had to develop. The other one, the big major one, is the motion planning component. We developed it with Tesseract. It's a motion planning framework that we've been using a lot of our projects. It fits our needs in terms of, the types of processes that we want to support. A lot of these material removal applications, Tesseract has been developed with those types of tasks in mind. So we develop our motion planning using Tesseract as the framework for it.
Okay, can I ask Joseph to clarify to the audience what is the Tesseract? Because I'm asking Joseph specifically because I know that he's been involved in the development of Tesseract.
Sure. Yeah, absolutely. Yeah, so Tesseract is a motion planning framework designed for robot arms, basically. Okay. So the whole point of it is that you're defining positions in the environment that you want the robot to go to, and then it figures out joint positions and velocities that define a trajectory that makes sure the robot visits all those points. And that's what other motion planning libraries, it's kind of common between all of that. Okay. So Tesseract is, it's fundamentally programmed in C++, although there's a Python wrapper available that exposes all the core functionality. And then it's available for both ROS and ROS2.
Uh-huh. Okay.
So we use it with those types of systems.
But you use Tesseract within MoveIt, or Tesseract is something standalone that is nothing has to be is not related to MoveIt.
Right. So yeah, it's standalone, right?
Okay.
So we find that some of the utilities that MoveIt provides, like for example the setup assistant for defining the robot definition files, those are you're able to use those like the URDF and the SRDF with Tesseract as well. That helps define the robot.
Okay, so then I'm asking you then for another interview in another podcast so that you can come, Joseph, and explain us about the Tesseract only. So for the audience, so they can understand better in more detail. I think it's going to be very, very interesting.
Yeah, it's extremely cool. Yeah.
Yes. Okay. So let's continue with the different parts that are composing this collaborative robot sanding. Jorge, can you continue? You mentioned the perception one based on PCL, then the motion planning based on Tesseract.
Mm-hmm. Sure. Then there was as for these sanding trajectories, we have to actually be in contact with the part as we sand the part, right? So that means a whole different way of executing a trajectory where you actually have to not only move through the waypoints of the toolpath, but you have to maintain a required force and move at a required speed, right? So that's something that hasn't been done in that particular way. And so we had to develop a whole new package to be able to, realize these motions with the UR, right? So it basically allows us to leverage the UR capabilities, the force feedback capability, to be able to execute those trajectories as required. And the other component was the region detection. So there is a stage in the application, after the first sanding step, where the robot sands the entire part or as much of it as it can.
Yes. And this is a moment for publicity. So your space here, if you want.
So there are parts of that sanding process where some areas didn't get sanded all the way. And so the operator has to go and circle those areas for rework. And then there's a system, with the same camera on the robot will go and take a new set of scans, but then it'll take those scans in order to find those circle areas.
Okay.
And then, there was a package that was developed to do that detection, which was built with OpenCV, which is a very powerful library for 2D images processing, and also the point cloud library. So it's like a hybrid component in that sense. And then that component is what allows the finding out or detecting these regions that were marked with just a simple Sharpie on the part. So,
and those are the ones that have to be sent.
Right. Yeah. So once those are identified, the robot goes and only sands the toolpaths inside those marked regions.
Okay.
For in order to finish the job.
Okay.
So those were the four major components of that particular project.
And that's one of the key things that really makes this a collaborative kind of system. And a lot of other robots, if you want to tell the robot where to go and do its work, you're sitting in front of a computer with a mouse and you're either clicking on, best case, you're clicking points on the surface. But a lot of the time you're typing new waypoints. So it's a very intuitive kind of process to just go to the part and draw on the part where you want the robot to do the work, and then the robot figures out what you want it to do based on that.
Okay. That was one of the questions that I was going to ask you, because everybody talks about this. So collaborative robots, and then but collaborative in which sense? Because I mean it's just an industrial arm robot, and I have to tell it to do everything. So in which way is collaborative? So then I think that you explained now one of the reasons.
Yeah, and then one of the other reasons is the universal robots arms have joint torque monitoring, so they can detect if they're colliding with something that they're not supposed to be colliding with, and they'll stop safely. So that means that we can sort of relax the safety limits around the area that the robot's working. I mean, it's holding a sander still, so you don't want to go and get in its way. I think It's kind of an aside point. I think people make a lot of assumptions about what collaborative means in a robotic context. It's probably challenging to make a truly collaborative welding robot, for example.
Okay. Yes. Okay, and then so you mentioned that before that you mentioned that it exists in simulation also. All this whole environment that can be tested also exists in reality. We are going to go to that point later, but so the audience can actually download all the packages with this simulation that simulates the real environment, right? And start testing what you are mentioning here.
Right. So basically, the software can be started in a simulation mode where, rather than starting or firing up all the driver nodes, right, the nodes that talk to the robot controller, it'll instead start the gazebo simulator. So that'll more or less be acting in the background as if it was a robot controller. So the application itself doesn't know whether it's talking to an actual robot or a simulator. It'll just talk to an interface.
Uh-huh.
And that enables this application to work with either a simulated robot in gazebo or an actual robot controller. Okay. But yes, it has the ability to operate in either mode.
Okay, and that's very interesting for the audience in terms that they can try right now. They can download it and try it. But then my question related to that is this simulation running in ROS2 nodes, or is a ROS1 gazebo simulation?
So Gazebo itself is a standalone software that can work with ROS1 and ROS2.
Mm-hmm. So
specifically as far as ROS2, you have to create
the Tesseract on your Tesseract.
You have to create plugins that allows Gazebo to either receive messages or publish messages into the ROS ecosystem, right?
Yes.
A lot of those plugins already exist for ROS1.
Yeah.
And some of those have been ported in ROS2. In our case, we had to implement one very simple for trajectory execution, in the ROS2 environment.
Okay.
But yes, you can run Gazebo in a ROS2 application.
Okay.
And one of the advantages of having Gazebo there, right, early on in the development cycle was that, obviously we didn't have all the hardware ready, we didn't have the camera and the robot, but we were still able to test the intermediate steps that we took in developing this application, as Gazebo is able to simulate sensor data and also simulate a whole robot, right? So you can see how your changes of the software reflect on the actual system to an extent, obviously, but having that ability to emulate sensor data was a huge help in being able to finish this development.
Exactly. I always explaining to the audience and to my students about the real procedure for developing for robots, which is start with the simulator, and they don't like that, because every one of us, we want to touch the real robot, but that's putting a lot of effort and delays, because it's more difficult to polish a program from the very beginning in the real robot. It takes a longer time than starting with a simulator. And then in this simulation, so you have built then the plugins that were missing for ROS2 and that you needed. So when we are running the sanding system in the using the simulation instead of using the real robot, then actually we are running the whole pipe in ROS2, right? In that case?
Yes, exactly. So at that point, the entire thing is working in ROS2. So the only time that we need ROS1 is if we're actually communicating with a robot controller. But for the simulation version, or for the simulator application, then you don't have to have any ROS1 components running.
Okay. And then for related to the part of ROS1, for you, more or less, you answer the question, but I would like to ask directly. So maybe Joseph can answer this one. It's about why do we need ROS1 in this application and how you solve it. This hybrid this hybrid application. How do you manage to do this hybrid application?
Yeah. So I'll draw a connection, I think, beyond this project to the whole ROS ecosystem.
Okay.
So the reason why people use ROS, right, is because there's all these different packages that people have written and released that supports different robots and different cameras and different pieces of hardware. And because ROS1 has been around for quite a long time, I think we're around over 10 years right now, right, Jorge?
More than 10 years. Yeah.
Yeah, so there's this huge body of work that's been developed to support all these different kinds of sensors, and one of the challenges with ROS2 is that your ROS1 systems aren't directly usable in ROS2. You have to do some work to modify the nodes and make them work differently so that you can run them as part of ROS2. And there's a big backlog of packages that have to be ported still.
Correct.
And it's a lot of work. It's a lot of work to do this. We've gotten a head start on some things that are very important to us, but it's a lot of work. So one of the important things that we need is the robot driver for the Universal Robots system. So that's a very well developed ROS1 package, that a lot of people use, but it's not quite ready to go in ROS2 yet. I can talk about this later. There's an ongoing effort to make a ROS2 version of this driver.
For the Universal Robot, you mean?
Yes, for the Universal Robot, yes. So, but in the meantime, we use the ROS1 bridge node to connect between the ROS1 node for the UR system and then all the rest of the ROS2 nodes for the whole system. So it allows us to keep going and do this development while we're kind of waiting on the driver support to catch up.
Okay, makes perfect sense. And actually, for all the ROS developers out there, that you have a lot of legacy code there in ROS1 and you are thinking about transferring to ROS2, then you can apply this trick right now and start porting all your code from ROS1 into ROS2 by using this bridge. So you can, for example, decide to change from ROS1 to ROS2 just a single part, just a single node. And then you can put it in ROS2 and it still communicates with all the rest of your ROS1 nodes that you already had by using this ROS1 bridge. That's what you have applied, right?
And it's been a very useful tool for us to do exactly that kind of thing.
Okay. And then I heard from Matt that, so I have used myself the ROS1 bridge, and we have done some live classes also on the internet about how to use it and how to configure. But we have been working with, let's say, toy examples because they are only the simulations and so on. You have applied this to a real robot, which is a Universal Robot 5. And then Matt told me, hey, so yeah, you can use the ROS1 bridge, but it makes a lot of difference how you configure it in order to achieve good success with your application. Can you tell me what is special with the ROS1 bridge that its configuration can affect so much with the final application?
Yeah, so this gets into how you kind of architect your whole ROS system, and the implementation of the bridge. So the way the ROS1 bridge is designed is it's a special application that is actually both a ROS1 node and a ROS2 node at the same time, and it automatically monitors the topics and services that are advertised on the ROS1 side and the ROS2 side. And for example, if it sees a new ROS1 topic being published by some ROS1 node, it creates a ROS1 subscriber for that topic, and then it connects that subscriber to a ROS2 publisher that's also on the bridge, and it kind of passes messages back and forth so to let them reach the ROS2 side of the system. So the challenge with this, though, is that if you have a lot of messages that you want to send between ROS1 and ROS2, they all have to go through this one node now, so it kind of introduces a bottleneck into the system. So I think my advice there, which is maybe a little ironic in the context of what we're talking about here, is I recommend minimizing use of the bridge node as much as possible. So your system will be more performant and work better if as much of it is in ROS2 as possible.
Okay. But if I remember correctly, then there is a configuration file that you can specify which topics you would like to be replicating. So actually, can you? And I'm asking you because I don't know. Is it possible maybe to have a couple of ROS bridge nodes, each one in charge of different topics, so we can kind of alleviate. So let's say the topics for cameras, they go on that ROS1 bridge node, and then we have another ROS bridge node that takes here for the point cloud data only here. I don't know.
Is that possible? I haven't used multiple bridge nodes in parallel before. Okay. It seems like you could do such a thing. One thing you alluded to is, yes, you can set the node to only bridge certain topics, which is useful. You want to kind of pare it down to the bare minimum. And then there is also an option to use the ROS1 bridge as, I guess you would call it a static bridge as opposed to a dynamic bridge. So when it's running in dynamic mode, it's automatically monitoring topics and creating connections and destroying connections as they disappear.
As they appear.
But as a static node, you can basically hard code it to only use specific topics, and that works. I think we found that to be, useful in some production systems. Where the environment is very clearly defined. We're not really expecting any new topics to appear somewhere, and we have to bring them over to ROS2. But I think the dynamic bridge is probably more applicable to a developer experimenting with this.
Yeah, because you don't know what to expect, right? You don't know what you are going to launch. You don't know. Makes sense. Okay, so I learned a lot here about the ROS1 bridge that I didn't know. And
one thing more to add on to as far as the bridge, right? It's not meant to be a long-term component in most applications, right? It's there for now during this transition of ROS1 to ROS2, but eventually the hope is that there won't be a need for ROS1 to ROS2 bridging or the other way, right? So as to encourage people to, port their packages and their code into a ROS2 environment. Yes.
Actually, there is going to be no more ROS1 in distributions.
Correct.
And I think that's the main motivation for why we're moving to ROS2 for all of our new projects is, because we want to be involved in the development of ROS. And, if we find things that we want to fix, we want to be able to, have, submit bug fixes and have those merged in. And it's the way to do that in the future is going to be by using a ROS2 system.
Exactly. Great. Then I have a question here that it's about the Tesseract, so the planning of the trajectories for the ARM. So you mentioned that Tesseract has nothing to do with the move it, and then maybe so not even related with move it too.
Well, the way that's related to Move It is both Move It and Tesseract use some of the same underlying libraries for motion planning. For example, there's a library called OMPL for the Open Motion Planning Library. It provides a wide variety of planners for like free space planning for ARMs. And so Tesseract uses OMPL and provides interfaces to the OMPL planners, as does Move It and Move It too.
Okay.
But Tesseract is it's totally independent.
Okay.
Of right.
Okay, and you had to develop the ROS2 packages of Tesseract for this specific applications, or you already had those in mind? Already built.
Well, we had those. We had them built as part of support for previous work. So one, I think, unique thing about how Tesseract is designed is that most of the core Tesseract libraries are actually completely independent of ROS. They're just pure, C++ CMake libraries. So you could actually bring those into a non-ROS system and have them, you'd be able to do motion planning there. But that means that in order to get So the ROS support for Tesseract is just a handful of packages and nodes that are kind of like a thin layer that sits on top of these core libraries. And so that actually made it very easy. Well, okay, it's not really easy. It was a lot of, anything in robotics is a lot of work. But it was just a few weeks of work to develop ROS2 nodes to support Tesseract to kind of duplicate the functionality of the existing ROS1 nodes. So we didn't have to go in and like re-architect anything really in the core libraries to get that working. So.
Okay,
that's something to add on to that, right? So in general, given that experience of how Tesseract was built, at least the core components as a pure CMake C++ library, we've adopted that mentality, that philosophy towards new packages that we develop, right? Where if there are core capabilities that we want to be able to leverage in either ROS1, ROS2, or any sort of framework, then we try our best to develop those core components in that particular way, where it's agnostic of.
Okay, it's agnostic. We are waiting here for Jorge to come back.
I'm back, sorry. Where it is agnostic of any kind of framework, and that way, using those components in other applications, regardless of the framework, it is made a lot easier. So it's one new kind of way of developing capabilities for robotics applications that we adopted.
Okay. So I don't know if I have understood correctly. Okay, so would it be something similar to PCL, for example, Tesseract? Would it be something like PCL? So PCL by itself, you can use it in any application. It doesn't matter from where the data comes. It's heavily used inside ROS because it has some integration and because it's very useful for robotics and especially in ROS. But by itself, you can use it in any other application, nothing related to ROS. Could it be that
that's
Tesseract?
a good comparison to make. Yes.
Yeah, that is a very good analogy.
Okay. So then I think I understood. Joseph wanted to add.
Yeah. So we did do some work in the Tesseract core packages. Even though they're independent of ROS, they have some features that make them easier to use within a ROS and a ROS2 context. Correct. So they have like package definition files in them, and they have like a ROS dep tags, so that you can automatically install the dependencies.
Okay. Yes. Okay. Great. And then. Okay, so I think we have answered many of the questions here.
One other thing I wanted to mention,
sure,
kind of tying into the CMake stuff. So one big reason why people are interested in ROS2 is because it offers support for Windows, right? In addition to the Linux-based systems that people have been using for a long time. And we've actually found that structuring our package in sort of like a quote-unquote pure CMake way actually makes it much easier to use those packages in a Windows environment. So that's kind of, we've been able to help ourselves out there because we're working with people who are interested in using ROS and Windows.
Yes, that's a very good point. So then Tesseract can compile now and run on Windows now.
Almost. I haven't used it on Windows. I think that's the idea. Yeah.
Okay.
I'm mainly a Linux developer.
Yeah. Yes. Okay. But then let me launch a call to the audience, to the ROS developers out there that are listening to the podcast. Then maybe you would like to try on Windows the Tesseract, and in theory it is ready to compile on your system. So you can give Joseph a hint, maybe your feedback, and tell him how it goes, how it works for you. Sorry,
it's still a very in development kind of thing.
Okay, then stay tuned. Then the call is stay tuned for Tesseract on Windows. Okay? Great. Then let me tell you about any other examples that you have been working about ROS Industrial within the ROS Industrial consortium, where you have been developing using ROS2, and maybe you need it also to use the bridge or not. Can you tell us any other example?
Yeah, so one other example, kind of relating to support for hardware. There are some specific 3D cameras that we use that don't have ROS2 drivers yet. So that's another place where we use the bridge in order to get the point cloud data from ROS1 to ROS2. Okay.
And then I think one question is not here on what I was expecting to ask you, but maybe for the audience, okay? So then maybe they are thinking, what these guys, they are using the bridge and looks like something complicated. Why don't they just write the driver for the robot, for the camera? What would you say to that?
Yeah, well, we're working on that basically. Yeah, so like I mentioned earlier, we're working with some of the other ROS-Industrial consortium members to develop a new ROS2 driver for the Universal Robots hardware. So that's taking advantage of some recent developments in the ROS2 ecosystem. So the ROS2 version of ROS Control I think it's been released now. Yeah, so that's a really important part that a lot of robot drivers are waiting on. So
yes.
So now that that's out there, we're beginning development of ROS2 driver for the Universal Robots robot. Okay.
Yeah.
So Go. I was just going to say that'll let us simplify a lot of our systems. We can have everything in ROS2 at that point, and it's very nice and clean and efficient.
And easier
Right. In general, as far as porting drivers into ROS2, right? It depends on how the original ROS1 driver was implemented. So, for instance, if you look at the code of any one ROS driver, you'll find like ROS info, function calls and things more for long.
Okay, I think that the camera, when he's speaking, is getting out. But,
sorry, okay. Sorry about that.
No problem. This is the direct, and I mean it's something that happens, and everybody understands.
It's the realities of our world, yeah.
So when that's the case, right? Like if the degree to which the ROS1 code is embedded into that application will dictate how easy it is to port that component into ROS2, right? So if it's mostly logging and maybe a message publishing, then that effort will be significantly easier than if there are other ROS1 components or code that's deeply embedded into that particular driver per se.
Okay, yes, and so and I also would like to put my experience on that. Why there are no, so it's easier to put the ROS1 bridge than writing the driver, because writing the drivers then and make them work, it requires a lot of work. It's very it's very difficult to make it work in a reliable way. Okay, so it's a lot of work that is stopping your actual work, which was to build, in this case, is to build the robot sanding application. In other cases, it's something else, and then making it work is not just a matter of hours. It's a driver.
Right. Yeah. There's a lot of reasons to go to ROS2, though, that I think make it something worth doing. In particular, the messaging middleware. People talk about DDS communication a lot. That's very well designed in ROS2 and offers a lot of nice features compared to what we're using in ROS1. As far as the defining target quality of service for messaging and actually making sure that messages are delivered when they're sent. And if you're using the bridge, that kind of gets lost in translation from ROS2 to ROS1. So that's why it's better to keep as much stuff in ROS2 as possible.
Yes, that's right. A couple of
and also, I think the lack of a ROS core is a plus as well, right? There's redundancy in your system by not having to depend on this one ROS core component that always has to be running. Otherwise, your application just dies entirely. And also, for me personally, I really liked coding my launch files in Python. I feel like they're so much more powerful as opposed to the way they were set up in ROS1 with XML files, right? So with Python, you're able to run things prior to actually launching your nodes. And so that really kind of gives you more power into how you stage your applications and what kinds of things you can do before an application is ran. And so that kind of, in fact, I don't see why I would want to go back to defining my launch files in XML.
Yes. Yeah.
That surprised me as well. I was a little apprehensive about the Python launch file situation in ROS2 when I first got started, but I really like it now, actually. It's like Jorge says, it's very powerful. Like we have some cases where there are files that need to live on the system in between running the ROS nodes, stuff for camera calibration. And now it makes it a lot easier to set up the system for the first run, because the launch file can check, do I have this file already? And then if not, it copies it from the package into some local directory, that it can use in the future. So that's been really cool.
Oh, okay,
Yeah, I
great.
mean, they can use the full capabilities of Python, essentially, right? You can bring all of the Python capabilities into your launch file. And so that, that gives you tremendous power.
Okay, yeah. So I'm still in the initial phase of Joseph, so that's still done. Okay, I'm still there. But I'm
a journey.
Yeah, I'm sure I'm going to be converted into loving this in Python launch file. And I wanted to mention that a couple of weeks ago of episode, I think it's right now, no. Is 4 episodes before we interview Mikael, who is in charge of the ROS2 packages, which are about securing a ROS connection. And also that is something important especially for industrial robots, that nobody can hack your application and make the robot do stupid things. This also will be lost if you are using the ROS1 bridge with all the messages that pass over there, because the security layer stops there on the bridge. That's what Michael explained. Yeah. Great. And then what else? So just to clarify, the audience can download your application from several Gits, right? That's right. Yeah.
So there's one main Git repository that has the instructions for how to build, and it'll also contain, a list of all the repos that are required. So, ROS has WS tools, right, which is a tool that allows you to pull in the various source dependencies. So there's a file in that repository that can be loaded into WS tool, and it'll automatically grab the various source repositories to build that project.
Okay, so I will ask you for that link afterwards, just in case that I don't have, just to confirm that I have the correct one. And then I will put all those links, including to all the things that you have mentioned, Tesseract, of course, ROS1 Bridge, and your own organization, ROS Industrial Americas, and ROS Industrial in general. And I will put it on the show notes. Okay, so then final question for each one of you. So let's start with Joseph, that he is here on the camera right now. So final question is, what is your opinion about the adoption of ROS and ROS2 in the industrial environment?
Yeah, so a big question that people ask me is, is ROS2 ready for industry?
Okay.
And I think actually the answer is yes, it is. I mean, we've been developing industrial applications in ROS2 for over a year now, and it's been going fine. It's been going just as well as any of our ROS1 projects have been going. So I say full steam ahead. I think we need a lot more developers, bringing in support for new pieces of hardware and kind of generally kicking the tires on things. So that's the next step we have to get into.
Okay. And what about you, Jorge? What do you think?
Yeah, same here. To be honest, I was when I was assigned my first ROS2 project, I was very hesitant that it was going to be ready for an industrial application like this collaborative robotics sanding one. And yeah, it was rough at the very beginning because I was not familiar with the framework. Things operated significantly different. The launch files were a whole new beast to me, getting used to this Python way of coding them and whatnot. But as I began to become more familiar with it, I realized that it is a very powerful framework, just like ROS1 is. And I feel like it is very much ready for use in industrial applications, like Joe was saying. And I feel like I would encourage people to start using it as much as they can in their projects. And, that'll only help advancing this framework to becoming even more robust and, feature complete than it already is.
And even surpass ROS1 and become the standard of the world.
Oh, yeah, absolutely.
Yes, we are here for that. Yes. Okay.
I have one thing I wanted to add on to something we talked about earlier. So we were talking about Tesseract on Windows. I went and I checked the build status in CI. It is building in Windows. Okay. In our testing pipeline. So I would encourage you to go try downloading it and building it. And If it works, awesome.
Great.
If you run into interesting things on your system, post some issues, and we'll get it fixed.
Okay, great. So all those ROS developers there using Windows. That's the call. So forget about the previous calls. Now the final call is go and test Tesseract on Windows and let Joseph know about the status, any issue, do your pull request also, and so on. And so that's it. That's for today. Thank you very much, guys. It was very, very instructive and clarifying. And I was very excited to see that kind of application using ROS doing an industrial. So there is the actual videos on the link I'm going to put the videos that they show the actual real robot using your system, right?
Correct. Yeah, that they do.
Okay. So then I tell to all the listeners to go to those links and check it in case that you want to see that in real life working. And that is all for today. Thank you very much for coming to the show, Jorge and Joseph.
Thank you, Ricardo. It's been great talking with you.
Thank you for the invite. It was great.
And for all the ROS developers out there, let me remind you that we are on a quest for increasing the number of followers. Of people that is listening to the podcast. So please give us a hand. Give us a hand and help us to reach to more people. Tell to your colleagues. Put a link to the podcast in your webpage, in your Twitter, and tell them how nice is this podcast and how many errors I do while I'm speaking. That's also a motivation for them to come and count and tell me. So please help us on that. And yes, that's all for today. So thank you very much for listening to the podcast, and see you next week with a new lesson from the experts. And until then, keep pushing your ROS learning. Okay, so here we are. So finished. Cool.